Right, good morning, everybody. Okay, so you're welcome once again to our physics class. Alright, so this is the second part of the video on photoelectric effect. So I've established the fact that photoelectric effect is actually the way, because the word photo here means light and electricity. So it's the way we can generate electricity from sunlight. So I've explained the concept, how that we have our Albert Einstein equation to the energy of photon, and I said photon is defined, all right, or is a discrete particle of light is equal to one function plus kinetic energy. So we have the equation hf is equal to hf naught plus the kinetic energy, all right, and I said that our h is the Planck constant, f is the frequency, and f naught is the special frequency, while our ek here is the kinetic energy. So I told you that our c is equal to f lambda, all right. This c is the speed of light, then this is the frequency of the wave, then multiplied by wavelength. And c is also equal to f naught lambda naught, all right. This is in terms of the speed, the frequency, and the light and the wavelength. While this in terms of the speed, the threshold frequency, and the threshold wavelength. So if you impute that, you are going to be having at the end of the day, if you make lambda is the formula for the first equation, you have lambda is equal to c over frequency. Now, so anywhere I see frequency, I'm going to be writing hc over lambda, all right, because c is equal to f lambda. So if you make lambda is the formula, you have c over f. If you make f is the formula, you have f is equal to c over lambda. So anywhere you see f, write c over lambda is equal to. So the value of hf naught here, f naught here, once f is equal to c over lambda, then f naught is going to be c over lambda naught. So at the end we have hf naught. Sorry, this is now hc over lambda naught, then plus the kinetic energy. All right. Now this Planck constant, this speed of light, this is the wavelength, this is the speed of light as well, and this is the threshold wavelength. Why this one is the threshold frequency? So if you move on, your kinetic energy in physics is supposed to be given to be Ek is equal to 1 over 2 mv squared. And in the previous video, I said that your kinetic energy, because what you're using is a light, so that mass becomes the mass of an electron that is ejected from the metal plate, then v squared. So you have hc over lambda is equal to hc over lambda naught plus anywhere you see your ek is now going to be 1 over 2 me then v squared. All right. So from that end, you are going to be having. All right. So you are going to be having hc over lambda is equal to hc over lambda naught plus 1 over 2 me. This mass of electron, then this velocity all into square, all into power 2. This was the final value we derived, all right. And I told us the definition that your energy that is transmitted from the light source called the energy of photon, while the energy required to eject the electron from the metal plate is what we call the work function, okay. And the last part is what we call the kinetic energy, which is the energy that the electrons are moving by. So you have this sunlight, and I should use this illustration as an example in the last part of the class. So that is that by the way. So but for today, we want to look deep into the other things we have in photoelectric effect. So the first thing we want to look at is what we call the X-rays. All right, X-rays. Now when you are talking about X-ray, what is X-ray? In your spectrum, all right, or what we call it electromagnetic spectrum, electromagnetic wave, you have two kinds of wave. You have a mechanical wave, which needs a material medium for propagation, and you have electromagnetic wave, which does not need a material medium for its propagation. So you find out that you have R, M, I, V, U, F, G. All right, these are the spectrum with increasing frequency but decreasing wavelength. Okay, this one is the radio, this is microwaves, this is infrared. All right, this is visible light, this is ultraviolet ray, this is X-ray, and this is gamma ray. So X-ray was discovered by a scientist called Röntgen. All right, Röntgen discovered X-ray in 1875. He kept actually some photographic plates, and when he came back in the laboratory, he found out that the photographic plate has become fogged. All right, and he traced to find out what happened instead of just throwing them the photographic plate away. So after tracing, he found that the fogging actually was as a result of the cathode ray. Okay, cathode ray. So that is how X-ray was generated, because you must have heard before that X-ray was accidentally produced. All right, so it was as a result of the photographic plate that was kept down that become fog by Roentgen in 1875. So that it traced to a cathode discharge tube. All right, it was thereafter he was able to know that X-ray can be gotten from that. Okay, so now what are the use of X-ray and what are the properties? Of course, X-rays move in straight line, and there are other concepts of X-ray like they are nice gases, they can penetrate wood and papers, they can penetrate glasses, all right, and the others. And X-ray is used in medicine, all right. We use it to take the snapshot of a bone. Maybe if somebody has a fracture, you can use X-ray to snap to know which particular area is affected. So that is basically that. Then, aside from X-ray, the other part that is very important in this aspect of quantum physics of the electric wave is what we call the wave particle duality. Wave particle duality. So when you are talking about wave particle duality, you must have heard of what we call duality of matter before. What is duality of matter? When you hear dual, dual means two, all right? So duality of matter is actually a way, all right? Light, because you are considering light can exist or can behave as two different things, all right? So in the context, light can behave as number one, a particle, then number two, light can also behave as a wave. Okay, so the study of light as a particle and the study of light as a wave is what we call the duality of light, all right, or wave particle duality. Now, when you are talking about light as a particle and when you are talking about light as a wave, what are the difference? Now, if light is a wave, of course, you must know that any substance that possesses energy and momentum is called a particle. So we can see on the strength of that, number one, for us to know that light is a particle, light has, all right, it has energy and momentum. Energy and momentum. So that is the first, all right, definition of light as a particle. So the study of the two is what I call the duality of light. Now, the behavior of light as a wave, all right, we can say that light has velocity. We have velocity, frequency, and wavelength. Yeah, frequency and wavelength. We are studying light as both a particle and as a wave, and the whole concept is what we call the duality of light. Now, the first one, light as a particle, all right, is that light has energy and momentum. Then light as a wave, light has frequency and wavelength. Then number two, now we use what we call photoelectric effect, and Compton effect is actually used in this place. Photoelectric effect, and we have Compton effect as well. Photoelectric effect, we have a Compton effect. Compton effect. All right, then here we can say that light, all right, can undergo reflection. As a matter of fact, all the five properties of wave, light can undergo the reflection, it can undergo diffraction, it can undergo diffraction, it can undergo polarization, and light can also undergo interference. All right. So the first one, all right, or as the study of light as a particle is that light has energy and momentum, while the other way, and when it's a wave, light has frequency and wavelength. Then for here, we use photoelectric effect and Compton effect. Then in the second part of light as a wave, we can say that light can undergo reflection, diffraction, diffraction, polarization, and interference. All those five things I mentioned are called the five properties of wave. All right, that is what we call the wave particle duality, or the light behavior as both particle and wave, which is what we call the duality of light. Now, the last part of this tutorial is what we call the de Broglie effect. Right, this is just the second video. I've done quite a number of things in this place in the first video. We have the de Broglie effect or de Broglie equation. The Broglie equation was actually invented in 1925. All right, it was to study the electron diffraction. When you are talking about diffraction is actually maybe in wave, you must have heard that it is the bending of a wave around an obstacle. All right, so in the context of electron, it will be the bending, all right, of electron. So if you are talking about electron diffraction, de Broglie actually derived a value in 1925 that we use in calculating for the de Broglie wavelength. All right, so anytime you are asked to derive de Broglie wavelength, de Broglie concluded that your lambda is equal to Planck constant over momentum. All right, that was what we have for de Broglie's equation. We have lambda is equal to Planck constant over momentum. So if you continue to find the wavelength that de Broglie later generated from the whole of that his experiment, We have lambda is equal to h momentum,